Good morning, everybody. My name is Paolo Piccinini. My tutor is Professor Andrea Prati, and my co-tutor was Professor Rita Cucchiara. This morning, I'm going to talk about the research activity I've carried out in this year, and I work mainly on a video surveillance application and on an industrial application. As a video surveillance application, I develop a smoke detector system, and as industrial application, I develop a beam picking system for cosmetic and pharmaceutical objects. Now, let me start talking about the smoke detector system. Since I spent only a few months working on this project, I'll give you only a short overview. And as you clearly see, this system can distinguish between generic moving objects such as people and cars from the smoke that propagate in the scene. And this system is based on two main features: the energy variation of the background in the wavelet domain and the color model for the smoke. When the smoke propagates in the scene, the energy of the background tends to decrease, and its color tends to blend with the color of the smoke. Combining together these two features with a Bayesian classifier, the system is able of detecting the smoke. This system was tested over 50 clips. I report here the result achieved only in the first 15 as example. And in the gray column, you can see the video type and the length expressed in number of frames. The video were taken on both indoor and outdoor scenarios. This must be yellow, and this is the result achieved using only the energy analysis, while the other column, called color analysis, show the result achieved using only the color analysis. Finally, the last white column shows the result obtained combining color and energy analysis. The label TTD stands for time to detect and represents the number of frames needed to detect the smoke since it appears in the scene, while the label FP means false positive and represents how often the system detects the smoke even if it is not present in the scene. As already said, was tested over 15 clips, and in 77% of the case, the smoke is detected in 3 seconds. In the 98.5% of the cases, the smoke is detected in 7 seconds, and the system always detects the smoke in 10 seconds. This is a simple video. Maybe you could see this white square that represents where the system records the energy variation in the background, and usually distinguish between the smoke and the people. And when the smoke is detected, it became blue. In these cases, this person became blue just because it is a unique moving object and not an error in a classification. Now, let me start talking about the main topic of my PhD, the beam picking system for cosmetic and pharmaceutical objects. And this project was developed in collaboration with Marchesini Group from Pianoro in Bologna. The beam picking problem can be defined as the automatic unloading of unsorted object from a bin to the next step in the manufacturing process. Before boring you with the full explanation of this system, I'd like to show you this video. This is the very first prototype in development at Marchesini facilities. Here you can see the robot that pick up the object. These are the camera used to recover the object position in the bin. Here there are some examples of picking, and please noting that when the objects are released, are always released with the same orientation. In the bin, you can see that the objects are very overlapped with each other, and how cluttered is the scene. So, finally, moving to the PC that manage the robot. In the monitor, you can see that there are some green bounded objects. Those are the detected one from the system, and the object selected to be picked is selected among this. This is a sketch representing the whole system. This sketch was taken from the patent related to this project. And the objects are dropped in a bulk on being placed over the conveyor belt. The conveyor belt brings the bin in the picking station, where two cameras acquire a couple synchronized image. And from the image, the 3D coordinate of the selected object are computed and sent to the robot. Finally, the robot picks up the object and places it in the placing station. Developing the system, I faced several challenges. Here I report the most important, and this is the first. Usually, when I've been picking system born for a specific target object, the picking policies and the object detection algorithm are strictly related to this object. In this case, I must be able to pick up several different kinds of objects, and I have to find a very generic algorithm. This is another challenge. As I already said, this system was projected for working on cosmetic and pharmaceutical objects. Cosmetic objects are usually characterized from shiny material and low texture, while pharmaceutical objects can be simultaneously semi-transparent and wrapped in flow pack. Reflexes are one of the major problems in computer vision because they drastically distort the object appearance and complicate the comparison between the object model and the object in the current scene. Moreover, semi-transparency is another major problem because it alters the object appearance, and when the object overlap, their appearance depend from their degree of overlapping. Random object disposal, multiple instances, and distractor, and heavy occlusion do not need to be explained because they were clearly visible from the video. Finally, this system must work with a very high picking rate. In fact, must be able of handling more than 100 objects per minute, and thinking a real competitor produced by Visual++ is very fast because the system proposed by Visual++ employ only more than a second just to the laser scanning of the bin. This is where the innovation related to this project rely, because must work with very different kind of object and without information such as CAD model or similar. And here I report a subset of the tested object using for testing this system. This is the system functional diagram, and this system is composed by four main blocks: object detection, object selection, three-dimensional localization, and object picking. In object detection, an image is acquired from the camera and used to detect the object in the bin. If no one object is detected, the system check the bin. If the bin is empty, is refeed. Otherwise, is shaken in order to change the object disposition. One or more objects are detected, the system goes to the object selection phase when only one object is selected to be picked up. Finally, in three-dimensional localization, exploiting a couple of stereo images, the 3D coordinate of the object are computed. Finally, the object these coordinates are sent to the robot that pick up the object. In this presentation, I discuss only the first three blocks because the object picking was not my responsibility. Let me now start talking about the object detection. The main goal of this block is to detect how many objects as possible in the current image. To do that, we choose of dividing this block into phases. feature extraction and matching, and object localization. In features extraction and matching, significant features are extracted from both the current model and from the model and the current image, and matched together with proper similarity measure. This is done in order to compute a set of correspondences. In the object localization phase, this set of correspondences is divided in subset, and the registration transform between the object model and each subset is computed. This is an example that clarifies what I have already said. Maybe the quality is not so good. This is the object model, and this is the current image. First of all, we compute the feature from both the current image and the model. Thank you. Then a number of principal points are manually fixed on the model, and among these, the most important is the center of mass, here depicted in white. Then the vector distances between each key point and each principal point are computed and stored. Then the features are matched together, and for each match we report at first the vector distance related to the center of mass. We cluster this center of mass, and if a cluster has a sufficient number of votes, this means that this is a potential object, and for each potential object we report the other principal point, and we finally compute the whole shape of the object. Now, let me move to talk about the object selection block. With the method just described, I'm able of detecting several objects in the current image without taking into account potential erroneous segmentation. The goal of object selection block is to remove from the list of the object from the list of the selected object potentially erroneous segmentation and the occluded object. We practically found two types of erroneous segmentation. We call the first type shadow segmentation, and are depicted here, while wrong segmentation are very wrong segmentation, detect an object where there is no one, and is depicted here. To get rid of shadow segmentation, we use a very simple empirical rule, while wrong segmentation are removed using a method based on a color similarity, and this is the similarity measured used here. Usually, each beam picking system tends to pick up the topmost object. Because this system is not always able of detecting the topmost object, we choose to pick up the non-occluded one. And so we need a method to detect occlusion. To detect occlusion, first of all, we need two segmentation. And given these two segmentation, we need to understand which is the topmost and the lowest object. So, given these two segmentation, first of all, we compute the histogram of gradient orientation in the overlapping region. Then the same histogram is computed for the first object, and finally is computed for the second object. Then we compare the histogram given from the overlapping region with the histogram given from the other two objects, and the most similar represent the topmost object. And this is a way of manage this kind of occlusion. Now, let me finally move to three-dimensional localization. Three-dimensional information have a double value for this system because allow the system to compute the 3D coordinate of the selected object and take care of occlusion when the occluded object is not detected. Recovering 3D coordinate is not an issue because it's a well-known problem and is already solved in many cases. Moreover, it's more interesting understand how to remove the occlusion when the occluding object is not detected. To do that, we exploit the information given by the disparity map, and we compute. And given the object segmentation, we compute it whole average height. Then we compute the average height in a smaller region surrounding the picking point, and we compare these two values. If the difference between these two values is lower than a certain threshold, that means that the object is not occluded and can be picked up. Otherwise, the object is discarded, and we go to the next step. We return at the first block. These are the list of several methods tested in order to recover three-dimensional information, and among these we choose of using sum of square differences because give us the best results. And these are some examples of disparity map computed from this system. Because the requirement of working in real time, we choose implementing the sum of square difference over a GPU, exploiting its great computational power. Finally, we have to evaluate this system, and in order to do that, we choose three different metrics: precision and recall at the object level, precision and recall at the pixel level, and accuracy of the center location. The first metric accounts for how many correct objects are detected in the current image, while the second metric considers a pixel-by-pixel segmentation, comparing the computed segmentation with a manually prefixed ground truth. Finally, the last metrics compute the distance between the projected picking point and its real position. These are a couple of examples of these three metrics. Of course, you can find many other results on my thesis, and the results reported here are for a syringe and a dropper. These are another example of segmentation. Of course, these images are too dark to be understood. And this is another evaluation matrix. One of the most important characteristics of the system is to always provide a catchable object to the robot. In order to do that, we simulate the picking process, manually picking the object. This should be yellow, and this must be the selected object to be picked up. And iteration after iteration, the system is always able of detecting an object or more than one, and is always able of picking up an object. Finally, this is my list of publication in international conferences. In journal, this is the part related to the beam picking process, and my last submitted publication. Many thanks for your attention. Any question?